It is now my distinct privilege and pleasure to introduce to you your King of Sprottania on Mars, from on high on Mount Olympus, King Peter Wykes.
Good afternoon, fellow Sprottanians. I'm so glad you could join us here today for this wonderful event. Normally, we are at home watching television and the Wonders of Physics show beamed to us from Earth. But I have a surprise for you today. I have invited Professor Sprott to come to Mars and visit us and show us some of his wonderful demonstrations. And if you look up in the sky, you can see him approaching now.
Welcome to the Wonders of Physics. Now, we've taken our show to Portugal and Egypt and South Africa and Japan, but this is the very first time I've ever been to Mars. And it's a great pleasure to spend our 30th season with you here today. And thank you for preparing this atmosphere that I can breathe. And I see you've prepared some of the demonstrations that I requested.
Yes, well, welcome, Professor Sprott, to Sprottania. As you know, we have named our city after you. In over 30 years, you have told us that there are 6 areas of classical physics. And it took you quite a bit of motion to get here today. And, you know, maybe there's a favorite motion demonstration you could show us today.
Well, you know, asking a physicist for his favorite demonstration is a little like asking a child which is their favorite parent. I like them all, but there is one that is very popular back on Earth. And if one of you Martians would help me, I can demonstrate it to you. Okay, come down here. Okay, turn around. Tell us your name.
Damon.
Damon. That's a good Martian name, Damon. Now, Damon, I know on Mars they have sports. Are you good at sports?
Mm-hmm.
Oh, great. Have you ever gone bowling, Damon?
Yes.
Bowling? You know that sport? We're going to take you bowling today, Damon. Turn to your right and go over to King Wykes. And we're going to make what we call a bowling ball pendulum. A bowling ball is a heavy ball on the end of a wire suspended from the ceiling. Now on Earth, a bowling ball like this weighs about 16 pounds. Here on Mars, it's only about 6 pounds, but it's very heavy. And we want you to, oh boy, we're going to have to help you a little bit. We're going to hold this, and when I say I want you to let go, and then put your, are you ready? Okay, now let go. Put your hands down by your side, and don't move. Thank you, Damon. Now, you know, when we do that experiment back on Earth, the bowling ball goes out and comes back about 60% faster because we have almost 3 times the gravity on Earth that you have here on Mars. And I've been enjoying this Mars gravity quite a bit. I feel very light on my feet, and I was wondering how high I could jump here with my Earth muscles. And so to keep me from injuring myself, I'm going to ask King Wykes to attach a rope to me. And then I'll just see how high I can jump. So let me scooch down and see how high I can go. Do you want to see it again?
Well, Professor Sprott, I see you've discovered how weightless you feel here on Mars.
Oh, it's great.
And indeed, our gravity is much less than that of Earth. And we have a physicist who has been studying motion, and he'd like to come out and show you some of his findings. So I present to you Mr. Ed.
What was that noise that you made?
Oh, that's an old Earth joke. Pay no attention.
I got a pitch. It sounded like Morse code.
No.
Never heard of Morse code before? Mars horse code?
Oh, yeah.
No? Okay. Anyways, motion is a pretty cool thing, and they thought that I'd like to meet you, Dr. Sprott, because I've heard you're quite the avid dancer.
Oh, I love to dance.
I'm also working on some things. The late Earth King that you might recall, I think his name was Elvis Presley. He is my mentor now. He moved here in the late 70s. He's a great fellow. Anyways, dancing is a really cool motion, but so are some other ones that are a little more easy to talk about. And the first one I want to talk about is straight line motion. Okay, so in my hand here, I have a tube that had open outside. And outside is the Martian atmosphere, which is about 1% as dense as Earth atmosphere, which is in this room. Now on Earth, they have these things called pennies and cotton balls, and I've got one of each in this tube. Okay, and that was thanks to NASA and Curiosity. Now, with only 1% the amount of air in here, when I flip this tube, you see that the two fall at about the same speed. Okay, and I'll do it again the other way. Okay, and they fall and they hit about the same time. Now, when I open the valve and allow the Earth atmosphere to enter the tube, you can see the cotton ball dance a little. And when I make the race again, the penny wins by at least 3 or 4 times the speed. Now, straight line motion is a lot of fun, but as a dancer, I have to be well practiced in my rotational motion. I got to spin every now and then. Still working on it. So, here I have a rotational platform of science. Okay, and I'm going to stand on this. Okay, now, there's a famous earthling that you might have heard of. His name is Isaac Newton. And Isaac Newton came up with 3 laws to govern motion. Okay, and the first one says, as long as I don't push something or something pushes me, I'll sit still or I won't start moving. But that's boring, because I can stand here and just do nothing, or I could do something more exciting. Now, his second law said if something pushes me, I'll start to move. Okay, so Dr. Sprott, would you maybe start my moving here?
Sure.
Okay, so it's a lot of fun, moving and spinning and so on. But I want to stop, because I get dizzy pretty quick. Okay, so what I'm going to do is use Newton's third law, which said if I push something one way, it'll push me the other. So I use this rocket to stop myself. Pretty fun. Ready? Okay, now after such a dizzying performance, I think it's better I stick to something a little simpler after that. I've seen Earth magicians on the television here for a long time, and they have this thing they call a trick, but I think I can pull it off. I have here a beaker of Mars water. Now this stuff is rare, okay, so I don't want to spill any during this. I want to pull the silk cloth out from underneath it. Okay, now who should shout out some suggestions? How should I do this?
Pull it down.
Pull it down. Well, the table's in the way. Okay, pull it down. Anybody else? Just shout it out. Downward motion. A lot of downs. All right, we're going to try the down. Here we go, all right? Fast. All right. All right, well, thank you, Dr. Sprott, for coming to Mars, and I hope you enjoy the rest of your stay. I'm a judge for this year's Dancing with the Martians, so I have to be off.
Well, I'm sure a lot of those dancers are really going to heat up the dance floor. And speaking of heat, you know, being the king, I have to wear all of these kingly robes, and it gets quite warm wearing all of this stuff. And, you know, heat is another area of classical physics. Maybe you could show us one of your favorite heat demonstrations.
Well, heat is important, and you know, I've been pretty cold since I came here to Mars. Back on Earth, we're closer to the sun and it's warmer. But I want to show you something that's colder than your very coldest winter night here on Mars. I have it in this container. It's a liquid. If I pour it out, it looks a little like water, except it doesn't make things wet. When it comes in contact with the table, it evaporates right away. This is something we have a lot of on Earth. It's called nitrogen. Most of the air we breathe is nitrogen. And when you cool nitrogen gas down to a low enough temperature, it becomes a liquid. So this is a liquid at a temperature of 321 degrees below 0 Fahrenheit, or 196 below 0 Celsius. And there are many interesting things we can do with it. One thing I want to do is to take a little stainless steel cup and lower it down into the liquid nitrogen. And it causes the nitrogen to boil. And that's because the cup is at the temperature of the room. And so it is much warmer than the liquid nitrogen. It heats it up and causes it to boil. Now, after a little while, the cup will cool down to the very low temperature of the liquid, and the boiling will stop. Once that happens, I'm going to be able to remove the cup, and it still has a little liquid nitrogen in it. I can shake it and spill it, but I don't want to spill too much, because I want to lower it down into this brass cylinder, take a cork and hammer it on. And then I'll just take the whole thing and shake it.
Well, that went off with a bit of a bang. If I heard correctly, Professor Sprott was talking about heat. I am the Martian steward of the land, wind, and water, and I am all-knowing when it comes to things hot, cold, or in between.
Well, now wait a minute. Land and wind I see lots of here on Mars. But water? There are no rivers or lakes here.
Please, don't let the king hear you mention that. He's still very angry at my predecessor for what happened to the water. Still on Mars, we have some princely things. As every Martian child knows, Mars has the solar system's tallest known mountain. It's an extinct volcano named Olympus Mons. It is 3 times taller than Earth's puny Mount Everest, thanks to our weak gravity. Dear Professor Sprott, many Martian children have enjoyed your Wonders of Physics show. Some have even braved this thick, dense, Earth-like atmosphere to be here. Some, I know, are quite shy, and I think I know where they're hiding. Come out, wherever you are. There they are. Come on, you want to see the show just like everybody else. Here they are. We'll put them up. Turn you around. This one's quite shy. Now, these children are budding scientists. They've been hard at work collecting an odorless, colorless gas named methane near Olympus Mons. It is often seen on Earth, near Earth's volcanoes. Now, because it's odorless and colorless, you can't see it and you can't taste it, but we have a demonstration here. There's a tank in the back. I'll open the valve here and bubble that methane through this soap solution, and we'll see what we get. Ooh, do you like bubbles? Yeah. Now let's see what these bubbles do. Let's see if it'll work. It's getting bigger. We'll just help it along. Oh, very nice. Methane is less dense than this Earth-like atmosphere, and so it floats. There's another property of methane that I want to show you. And I have to light my candle, but I'll probably use the match for this. Yes. In the presence of an oxygen atmosphere, methane burns. Should we try that again? Yeah. Okay, let's try it. Let's cut up that bubble. Oh, here it goes. Right now, we'll do an experiment that shows us what the atmosphere in this room can do if we allow the water vapor, the steam inside this container, to turn back into liquid. So we will turn off the heat, which I just did. We will seal this valve nice and tight, and then it's going to start to cool down. That water vapor, that steam, will condense back into liquid, and when it does, it will shrink. It will shrink about a factor of 2,000, leaving a vacuum. And now you'll see what the air pressure in this room will do to this very hard can. Let's see, it takes a while sometimes. There we go. It's shrinking. The can. And will we get, little help. Now, you don't feel this pressure from this Earth-like atmosphere, but it's there. And we have another demonstration that allows us to compare the Martian atmosphere pressure with the Earth atmospheric pressure, and that's a demonstration over here in this long tube. But before I run the demonstration, I will need a volunteer from the audience to help me out with this special can of Martian dew. Martian, see? Let's see who will come up. Little boy in the fluorescent neon green, come on down. Are you really strong? Do you think you could crush this can?
Which way?
Which way? What's your name, by the way?
Kellen.
Kellen? That's a nice name. Which way? That's a good question. It's first person. With a ping pong ball. All right, stand over here. Throw that ball as hard as you can to crush that can. Thank you. Try again. You can get as close as you want so you can hit it. Let's get a good hit. There you go. Did you crush it? A little bit. Well, he made a dent in it. That's good. But we'll try to do better. Thank you very much. So we will put this can back in the little holder. And we have another ping pong ball right here. And right now in this tube, the pressure is the same as it is in the room. But when I ask, please, Professor Sprott, turn on the pump, we are now pumping the air out of the tube. It has windows that hold the vacuum inside, and I can watch this gauge, and when it reaches the pressure outside of our dome on the surface of Mars, then we will perform a little second experiment. We will remove the safety, we will push this plunger, it will break this plastic, letting the Earth-like atmosphere on one side and the Mars-like atmosphere on the other, and that force from the air pressure will speed up the ping pong ball. We'll see how fast. Good job holding your ears. Very good. I'll need a countdown. 3, 2, 1, go! We did a little better. Well, I'm crushed that my time is up, Professor Sprott, but I have more work to do near Olympus Mons. It would appear there's some rumbling sounds coming from it. Maybe it's not so extinct after all.
Well, Professor Sprott, he sure was a noisy fella. You know, I like things to be very quiet, and here on Mars, since we have such a thin atmosphere, sound does not travel very well at all. So when I'm outside playing golf, it's nice and quiet. But I understand on Earth you have a lot of birds that must be really noisy when you're playing golf. So anyhow, sound is another area of classical physics. Maybe you could show us one of your favorite sound demonstrations.
Well, you know, it is noisy back on Earth, and it sometimes bothers me too. Not so much the birds, but there's lots of noise that we have. You know, sound is kind of odd because you can't see it, but you can hear it, right? But sound is a form of wave, and there is a way for me to make it obvious to you that it is a wave. And I use this gadget right here. Do you know what this is called? That's right, an oscilloscope. And it's connected to this microphone, and so any sounds that come into here are displayed there, and you can see what a sound wave would look like if you could see it. And you see how complicated the sound is corresponding to speech. Now, not all sounds are complicated like that. Do you recognize this? What? A tuning fork. U-shaped piece of metal. You strike it with a mallet, it makes a sound. We're going to do it and look on the oscilloscope. And that's a very regular kind of sound. That's what we call a sine wave. It's the purest type of sound. It consists of a single frequency. In this case, it's 440 cycles per second. For you musicians, it's the note A. Now, speaking of music, back on Earth, we have things called orchestras. You have them here? Well, a bunch of people sit around with musical instruments and they play the same music with their different instruments. Now, one of the instruments that our Earth children often learn to play is a recorder. And I never learned to play it when I was young back on Earth, but I can blow a few notes and let you see what it looks like on the oscilloscope. And that's how you can tell one musical instrument from another, even when they're playing the same note, because every instrument has a distinctive wave shape associated with that particular device. Now, back on Earth, we have lots of sports, and sometimes the referee has a whistle, and when they want the play to stop, they blow the whistle. So let's look at this on the oscilloscope. Now, that's a rather complicated sound. Did you know there are sounds you can't hear? What's an example? A dog whistle, that's right. Do you have dogs on Mars? Yeah, we have lots of dogs back on Earth, and sometimes we train the dog to come when they hear this whistle. Now, the whistle is such a high pitch that most humans can't hear it, but the dogs can hear it, and you can train the dog to come when they hear the whistle. Now, I'm going to blow it. Some of you Martians may be able to hear it, but even if you can't, you'll be able to see on the oscilloscope that it's making a sound. So here we go. That's where Rover went.
Fly me to the moon.
Wait.
Let me play.
I hear music, but that can't be. We're on Mars. There's no atmosphere here on Mars for the sound to travel through, so I must be imagining things.
My apologies. My name's Mike. I'm the Minister of Sound here on Mars. I'm so excited to meet the great Sprott, I forgot to move my lips. You see, sound works very differently here on Mars, so we Martians have learned how to communicate directly with our brains. But we also have learned to move our lips to make Earthlings a little more comfortable.
Well, you know, sound is one of my favorite areas of physics. I want to hear more about this.
Oh, well, absolutely. Sound is a vibration in some material. And to demonstrate that, I have this coiled piece of wire back here. On Earth, this is called a slinky. In a sound wave, the material is stretched apart and pushed together. So you get a wave that looks like this. This is called a longitudinal wave. Now, sound depends on pressure, temperature, and the kind of material that the sound is moving through. On Earth, Earth's atmosphere is mostly nitrogen and oxygen. Earthlings call this mixture air. Now, the speed of sound in air is about 340 meters per second. That's almost 760 miles per hour. Frequency is how fast those sound waves travel past a certain point. Now, to demonstrate that, I've created this device. I call this a barsoom. I need a Martian child to help me with this. Who can I have help me out here? How about you? I think a good, this young lady right here. Come on down. What is your name? Molly. It's a good Martian name. Now, Molly, the way this works is the sound that comes out depends on the length of this tube, and it also depends on the gas that's inside. We're going to start off with some Earth air, okay? What I want you to do is push those two things together as hard as you can. Very good. Okay, that's good. Oops, so that's what air sounds like. Now, this balloon contains helium. Now, helium is a very light gas. The speed of sound in helium is almost 3 times faster. So the sound waves will bounce back and forth faster and make a higher frequency or higher pitch. Let's try this one out. That's very good. This balloon contains sulfur hexafluoride. It's a very heavy, dense gas, and the speed of sound in this is about 1/3 as fast as that in air. Let's see what happens with this. Yeah, the sound waves bounce back much more slowly, so you've got a lower frequency or lower pitch. This last one contains Martian atmosphere. Now, Mars atmosphere is almost completely carbon dioxide. Listen carefully and hear how it compares to the other gases. Now, what do you think? Do you think that's pretty close to air? Do you think it's a little lower, a little higher?
A little
Yeah, it was a little bit lower than air. Very good. You have a very good ear. And that's about right, because carbon dioxide is a little denser than air, so the speed of sound in carbon dioxide is a little bit lower than that of air, so we got a lower pitch. Molly, you did a great job. Thank you very much. Let's give her a big round of applause. Well, as I mentioned earlier, sound works differently on Mars than it does on Earth. This has to do with the density of the Martian atmosphere. Mars's atmosphere is very, very thin. So what we're doing here is we're pumping the air out of this large jar here to simulate Mars's atmosphere, how thin it is. We also have a sound-making device in there, a speaker, and a microphone. Oh, I should also mention I brought my pets along to help demonstrate today. This is Phobos, and this is Deimos, named after the Martian moons. I've been teaching them how to dance to Earth music. Phobos is getting quite good at it. Deimos just kind of sits there. Oh well, can't win them all. Anyway, what we're going to do here is we're going to play a little bit of Earth music through the loudspeaker in this jar. And we're going to hear what it sounds like through the thin, thin Martian atmosphere. Okay, hang on just a moment. Let's hear what it sounds like. Can you hear it? You can't hear it very easily, though. It's very, very faint, because the sound does not travel through that thin atmosphere very well. So what we're going to do is we're going to let this Earth-type atmosphere back in the jar. Let's see what difference that makes. Let me put this on hold for a second. Now we're letting the air back in the jar there. Can you help me out there? Can you see the numbers there? Let me know when that gets to 0. Getting close? 3, 2. I think we're almost there. All right, let's see what the difference is now. There you go. Come on. You notice how much louder it is now? Sound likes to move through materials. The denser, the better. The denser it is, the louder it'll be. So now you understand why we Martians learn to communicate directly with our brains. If we tried to talk to each other, even if I was shouting at the top of my lungs and you were standing right there, I could be shouting and you would barely hear me through that very thin Martian atmosphere. What are you doing?
I'm using my Apple computer to translate from Martian to English.
That's not an Apple computer.
Yes, it is. Steve Jobs was working on it just before he died, and he sent me the plans by email.
Oh, wow. Well, that's a fantastic invention. That'll really help us communicate better with Earthlings. Thank you for sharing that.
Hey, let me try some of that telepathic singing you were doing before.
Oh, please. Oh, no, not Mars by Holst. That tune is so played out here. I've got to go. Sorry.
Well, you know, that's really not an Apple computer that he was talking about. That was our Mars Mapple computer. And of course, we have M-Pads, M-Pods, M-Phones, and MP3s. And, you know, this all comes at a great cost to us because it demands so much electricity to power all of these devices. And by the way, do you know why a transformer hums?
No, why?
Because it doesn't know the words. But anyhow, maybe you could show us one of your favorite electricity demonstrations.
Well, we have lots of electrical gadgets back on Earth, as I know you do here on Mars as well. We have something you don't have. We have electrical discharges in the atmosphere of the Earth. We call it lightning. And I want to demonstrate that to you if one of you Martians would volunteer to help. Okay, how about you? Yep, you run on down here. And we're going to take you where there is lightning. Now, maybe you don't know about lightning. Turn around, face the audience. What's your name?
Eric.
Eric. Okay, Eric, have you ever seen lightning? Oh, you have. Does it scare you? Well, it should kind of scare you because lightning can be dangerous. But we're going to put you in a place that's very, very safe. Eric, turn to your left, walk over to this cage, and have a seat in what on Earth we call an electric chair. Now, over to Eric's right is a 1,000,000-volt Tesla coil, and it makes bolts of lightning. So as long as you don't stick your fingers through the cage, you shouldn't feel a thing. Thank you, Eric.
Greetings, Professor Sprott. I am Martin the Martian, Secretary of Energy of Sprottania. It is my job to ensure that all the Martians have enough electricity to watch your broadcasts on Wisconsin Public Television. And may I say that we find your demonstrations electrifying? Ha ha ha. We were particularly inspired by the demonstration of the Tesla coil. When we saw the sparks flying through the air, we thought perhaps we can transmit electricity that way. Do you think that is possible?
Well, you know, that was Nikola Tesla's early idea. He was going to make a gigantic version of one of these coils and send electric power all over the Earth without using wires.
Ah, well, perhaps we can try that now.
Sure.
If you would be kind enough to run the Tesla coil again, I will hand these fluorescent light bulbs to some of these Martians in the audience. Here, would you like to hold one? Take just one. And careful, 2 hands. It is heavy, but just one. There you go. Would you like one? 2 hands. Thank you. And you have one too. And I will hold one. All right. Strike up the Tesla coil. Ah, thank you very much. Well, it does take quite a bit of electricity to run the Tesla coil, but Professor Sprott has shown us many ways to generate electricity. For example, static electricity, like when you rub your feet on the carpet in the winter and then get a shock. We have a device over here called a Van de Graaff generator, which works on a similar principle. In the base, there's a strip of cloth that will run around and around when I turn on the motor. It will rub off electrons onto this metal sphere. Now on top of the metal sphere, I have an old friend. Professor Sprott, do you have pets on Earth?
Well, we have lots of dogs and cats.
I used to have a cat. Your Earthlander landed on it, and curiosity killed the cat. But we continue on in the name of science. Let me start up the Van de Graaff generator. And as electrons are transferred to the sphere and then to the hair, electrons repel each other because like charges repel. And so the hairs stand on end as they repel each other. I have here a grounding rod that will attract some of the electrons. So if I remove them, the hair falls back down. As you can see. It is the latest style on Mars. Well, thank you, Fluffy. Well, yes, as you know, we used to have great streams of water on Mars, but they are dried up or frozen now. But we once thought perhaps we would use the water to transmit electricity. Yes, water can interact with electric charge, and I will demonstrate this for you. I have here some Martian water. It is identical to Earth water in composition, except for the addition of food coloring. I have here an insulating rod. I will charge up the insulating rod by rubbing it with the fur of this Martian marmot. Now, then I will bring the rod near to the water, and we will see what happens. Ready? Now let us try the other side. Transferring electrons onto the rod, and then I bring it near, but not touching the water. And it is deflected. Well, Water can have other uses, for example, in rocket science. Yes, we enjoy rocket science here on Mars. Professor Sprott, do you know how to put a Martian baby to sleep?
No, how do you do that?
Well, you rock it. But many of our rockets use hydrogen and oxygen as their propellants, and we can get these from water. Yes, does anyone know what the chemical formula for water is? Please shout it out. H2O. That is correct. So every molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. We have a device here which performs electrolysis. A current is run through the water, splitting it into its hydrogen and oxygen. We have arranged it so the hydrogen is captured here on your left and the oxygen on the right. There is twice as much hydrogen because there are 2 atoms of hydrogen for every 1 atom of oxygen. But how can we test and be sure? What is a good test for hydrogen? Any ideas? Shout it out, please. Clever ideas for testing for hydrogen. Fire! You Martians are clever. Yes, we will test by fire for hydrogen and then oxygen. I will start by lighting 2 candles, and we will use them in our tests. Now, the hydrogen is lighter than air. So, what I will do is I will take a vessel and hold it upside down over the hydrogen, release the hydrogen, and capture it into this vessel. Then I will bring the candle near, and we will see what happens. All right, releasing the hydrogen. Now this vessel should be full of hydrogen. And the flame. A small explosion. Indeed. We had hydrogen. Now to test for oxygen. Oxygen aids in combustion, so what I will do is I will take this splint of wood and I will begin to burn it. Now once it has some nice red embers, I will blow out the flame and then I will bring it near to the oxygen and expose it to pure oxygen, and we will see what happens. So this is now burning, and then I will blow it out and expose it to oxygen. Make sure it is out fully, and then, the flame has been reignited by exposure to pure oxygen. Well, Professor Sprott, I must go and ensure that our generators are still running. Thank you for your time. Please say hello to your Secretary of Energy, Stephen Chu, a Nobel Prize-winning physicist. Goodbye.
Well, Professor Sprott, do you know what one magnet said to the other magnet?
No, what did one magnet say to the other?
I find you attractive. So anyhow, magnets are another area of classical physics, and we here on Mars have developed the very first magnetic levitated train. Although it was quite unsuccessful because of our weak gravity, it just sort of floated off of the tracks. But possibly there's a favorite magnetism demonstration you could do for us.
Oh, yes, indeed. You know, magnetism and electricity are closely related, but in fact, one way to make a strong magnetic field is with an electric current. And here I have a bar of iron surrounded by several hundred turns of copper wire, and it's plugged into the wall back here. And in a moment, I'm going to turn it on. Now here I have an aluminum ring. Now you know aluminum is not normally a magnetic material. Here I have a magnet. It's not at all attracted to the magnet. To prove it's a magnet, it easily picks up the nails. However, when I lower this ring down over the electromagnet and turn it on, that will induce an electric current in the ring. That will make this momentarily magnetic. And then this magnet will in fact be repelled by this magnet. So let's try that. That went pretty fast. Let's do it again. Okay. Now, would you like to see it go a little higher? Everyone says that. I don't know why. Here's an iron pipe, and that concentrates the magnetic field and makes it go up higher. So let's try it now. Now, there's another way to make it go high. I can put the ring in this little glass dish, and I can pour some liquid nitrogen over it. And this will give you a chance to observe the liquid nitrogen. And you notice it's boiling. It looks a little like boiling water, but it's not. It's nitrogen. And it's boiling because the glass dish and the aluminum ring are much warmer than the liquid nitrogen. Remember, 321 degrees below 0 Fahrenheit. And so that causes the nitrogen to boil. But in a little while, the ring and the dish will cool down to the very low temperature of the liquid, and the boiling will stop. At that time, I'll be able to remove the ring. Now, it turns out that aluminum, like most metals, is a much better conductor of electricity when it's cold than when it's at room temperature. In fact, aluminum is about a 7 times better conductor of electricity at the temperature of liquid nitrogen. So you would expect the induced current to be larger and the magnetic force to be larger. So it's just about stopped boiling, so I can now take it out and repeat the demonstration with the cold ring. Now, would you like to see that again? Okay, I see you Martians are good scientists. You like to do experiments, and that's the mark of a scientist. So let's try it with the cold ring and the iron core.
Salvete! Et solve Clintus Spratus, meus nomen Marses, Deus belli, quilagis.
Wait a minute, that sounds like Latin.
Oh, you speak Martian? Well, that was Latin. I thought all Earthlings knew Latin.
No, we haven't spoken Latin in 1,000 years.
Well, now I just feel silly.
Well, you look a little silly, but I'm glad you're here.
Well, I guess I don't need these. My name is Blaine. I'm the chief scientist for the Martian Department of Defense. You know, a long time ago, I was sent on a reconnaissance mission to Earth. Due to some poorly made crop circles, we took a wrong turn and crash-landed on a continent known as Europe during the height of the Roman Empire. Now, luckily, we had enough Martian dew to sustain us for the trip, and we shared some with the locals that we met. We found a really interesting effect on them, though. You see, it made them really strong and gave them increased endurance. Using Martian dew, Roman soldiers were able to conquer much of the known world. And since I was the one that brought it to them, they began to worship me as Mars, the god of war. Of course, I was in no position to correct them. Now, humans have since developed their own compound. They call it Mountain Dew, and it's not quite as effective. It lacks one key ingredient, stored magnetic energy. Would you all like to see how we put that ingredient in here on Mars? Yeah. Great. Well, we have one of the devices at the very end of the assembly line, so a full can of Martian dew would be put into this device. I have here an empty can, and we've hollowed out the bottom for a little more dramatic of an effect. Now, you'll see this large orange block here. This is what's called a capacitor. It's like a really big battery, but it discharges all at once. When I let go of this button, about 5,000 volts of potential will be released, and that current is going to run through this device where these copper windings are. Now, as it goes through those windings, it's going to create a strong magnetic field, and that'll interact with the electric field that's part of the current. When these two fields interact with each other, they create something known as the Lorentz force, which is named after a famous Earth physicist. Now, that force is going to act to pinch the can inward. And it's really dramatic and really loud. So if you're in the front row, I suggest you close your ears. Here we go. In 3, 2, 1. Pretty dramatic, right? Now, you'll notice it jumped out a little bit, and I'd like to see if we can make it jump a little bit farther. So I'm going to place the can in just a little bit differently. I got this idea from studying naval warships that the U.S. Navy uses. You see, they have a device called a railgun, which is a really long platform, and it uses similar electromagnetic energy to launch projectiles very far. Now, sir in the blue, it looks like it's going to be coming right at you. Yep. Everyone else, keep your head up just in case. Here we go in 3, 2, 1. Now, of course, had there been Martian dew in that can, the magnetic energy would have been stored in there for delicious nutrient later. Humans have been experimenting with fluids that react to magnetic fields also. They call them ferrofluids, from the Latin word ferrum, which means iron. I have here an example of a ferrofluid. It's just a bunch of small iron filings that have been emulsified in a liquid. And you can see it up here on the screen. It just looks like a plain liquid in a beaker. But as I bring a magnet near it, you'll see that the fluid will try to flow along the magnetic field lines. And if I flip the magnet around, it would be a little more dramatic. Pretty cool, huh? Now, ferrofluids like this are used in high-tech industrial applications as a sort of motor oil, especially like in the aerospace industry. Now, I have one more experiment I'd like to show you. Some of you may be thinking, if you have a floating train and you need to get it to stop, well, what do? There's no friction to use for braking, right? We can use magnetic forces for that also. I have here another magnet, and here we have a large copper plate. Copper is a great conductor of electricity. And as you'll see, whenever a magnet is dropping towards a copper plate, it creates a change in flux, which will make something known as eddy currents in the conductor. And those eddy currents will create a force that will try to oppose that change in flux. So what that means is it'll try to stop the magnet from falling. You'll see it falls pretty readily under the force of gravity, but as we drop it above the plate, it falls a little bit slower. Now, it's not so slow that it's a huge noticeable effect, but you all also learned from Professor Sprott that if we cool a conductor down, it's much better at conducting. So I have here an identical copper plate that we've placed in a bath of liquid nitrogen. And as you'll see, the eddy current should be a little more effective at slowing it down. Let's take a look. It takes a little bit longer to fall. In fact, even just tipping it over takes a lot longer. So this is the kind of mechanism we can use to stop the maglev train. Now, I'm told that on Earth, there's these great child warriors that'll lash together several chariots, and they call such a war device a roller coaster. This is the same principle that's used to slow roller coasters down at the end of their rides. Well, if you'll excuse me, we need to go plan our invasion of Venus, but I hope you've learned a little something about magnetic energy today.
Well, Professor Sprott, do you know how many theoretical physicists specializing in general relativity it takes to change a light bulb?
No? How many does it take?
2. One to hold the light bulb and the other to rotate the universe. Anyhow, speaking of the universe, one thing I do like to do when I'm up at the castle at Mount Olympus is look up at the sky and see all the beautiful stars that are there. Can you see stars on Earth?
Well, we sure can, but I've noticed that your stars here are especially vivid. And I think that's because of your thin atmosphere. On Earth, we have to look through a very dense atmosphere. Sometimes it's polluted, and it reflects light from the ground, and often it's very hard to see stars on the Earth. Our stars also do something that your Martian stars don't do. They appear to twinkle. Now, you may not know what that means, but I can show you with a little demonstration here. Here I have a laser, and I'm going to turn it on, and you can see that dot on the wall over there coming from the laser. Now, to prove that it's coming from the laser, I can just put a little spray here to illuminate the laser beam. And so, as you would expect, light travels in quite a straight line. But it turns out it doesn't travel in an absolute straight line. When it goes through the atmosphere, it bends ever so slightly. And the amount that it bends depends on the density of the atmosphere, which is determined by the temperature of the atmosphere. So if I can do something to warm the air here, I might be able to show you what it looks like when we look at the stars from the Earth through our dense atmosphere. So I'm going to light this burner, remind myself where the laser beam is. Then I'm going to put the burner underneath the laser beam and look at the dot on the wall over there. And that's what we mean by a twinkling star.
Greetings, Professor Sprott. We welcome you to Mars.
We are members of the Martian Light Brigade. We have found your demonstrations to be most illuminating.
It's our job to study how to do things with light. We'd like to show you some of the demonstrations we've learned from watching your show. The other day I was watching some Earth TV.
Don't watch too much TV, kids. It'll rot your brains.
It's very true. I was just watching a little bit of television, but I saw some Earth cities at nighttime, all lit up with very bright colors. And I noticed that some of these lights were caused by signs with letters on them. And I found out that these signs were called neon lights. And that another word for this is Geissler tubes. So I wanted to learn more about what caused this. And we made some to have here on Mars, and we'd like to show them to you.
So here we have our Geissler tubes. We just have a series of glass tubes, and each tube is filled with a gas such as neon. And what we're going to do is we're going to run an electric current through each of the tubes. And when we do this, the electric current is going to excite the atoms in the gases, causing them to glow. Take a look. Something else we have learned from studying Earth is that if you look at the sky on Earth, you will see that it is blue. And so we wondered, why is this? Why is it that the Earth's sky is blue? It turns out that the sky is blue because of something called Rayleigh scattering. When light from the sun, which is white light or all colors combined, when that light strikes the Earth's atmosphere, light that is more yellow in color passes straight through the atmosphere and comes to the ground, whereas light that is more blue in color bounces off of particles in the atmosphere before coming to the ground. So when you look up at the sky on Earth, you see the light that is more blue in color having scattered off of the particles in the sky, then coming to the ground, which you then see. So we're going to demonstrate this right here. We have a tank of water and a lamp here which is going to make white light. And we see the white light is projected over there on the screen. And what we're going to do is we're going to now mix some milk into the tank of water. And the particles of milk are going to scatter or have some of the light is going to bounce off of it. So we'll see in just a moment here that some of the light passes straight through, and that light is more yellow in color. We see there on the screen, whereas the light that is more blue in color comes straight out of the front of the tank after having bounced off of or having scattered off of the particles of milk. And so this is a demonstration of why the sky is blue.
So, when you look at the sun,
never look directly at the sun, kids. Very bad for your eyes, very dangerous. Don't do it.
it's a very good point. So perhaps if you look at a picture of the sun, you will see that it is yellow and the sky all around it is blue. Of course, this isn't true here on Mars. This is only for Earth. Here on Mars, our sky is actually more of a yellow kind of butterscotch color. So the reason for this is that our Mars atmosphere is different than it is on Earth. So the atmosphere is much thinner, and we have a lot more dust particles. So we have a more yellow sky.
Now, I have a very important question for all of you. Who likes to pop balloons? Oh, good. I was worried. What we're going to do is we're going to pop a balloon. But we're not going to pop it with a pin or by crushing it or squeezing it. We're going to pop it using the power of light. We have a laser here that I'm going to turn on. You can see the laser. I'll bring down the lights. And so now what we're going to do is we're going to put this balloon in a box and then shine the laser at it and see what happens. Here we go. 3, 2, 1. So what happened? The balloon absorbed the light from the laser, causing the balloon to heat up, and this caused it to burst. Would everybody like to see that again? Yeah! Ah, excellent. Well, we're going to do it again, but we have something slightly different this time.
So what we have here is we have a balloon inside of a balloon. So what do you think is going to happen if we shoot the laser at this balloon, these balloons? Will one blow up but not the other? Will they both pop? Should we find out? Let's see.
Yes, we should find out.
Let's see what happens. In we go.
Okay, here we go. 3, 2, 1.
So what happened here? Well, the inner balloon has popped and the outer balloon is still all inflated. So why is this? The outer balloon is a clear kind of color and the inner one was purple. So the laser just went straight through the transparent balloon and heated up the purple balloon so that it popped, but the clear one did not.
Well, we have been delighted to share our knowledge with you.
Unfortunately, that is all the time we have. We must go now. Light Brigade,
charge!
Well, Professor Sprott, I want to thank you for coming and visiting us here on Mars and showing us some of your demonstrations. And I think all of us Martians should give Professor Sprott a very loud applause for giving us 30 years of wonders of physics. Thank you very much, Professor Sprott. Now, another thing that I'm very fond of looking at pictures of are clouds. And maybe you could show us something about clouds.
Well, we do have beautiful clouds on the Earth. You may not know what those are, but they're white puffy things that are up in the atmosphere. And in all of our shows, for 256 presentations, we've always concluded by making a cloud to show you how it works. And in order to do that, I have back here a tank of liquid nitrogen, the same stuff we used before. But it's a very large container. It's 25 liters of this liquid. And what we do is force the nitrogen gas into here. That forces the liquid up into this pipe on the top, which has about a dozen holes on the top. It comes out and it cools the air. And when that happens, the water vapor in the air condenses into tiny droplets of liquid water. And that's what we call a cloud. And so, with that, I'll take my helmet. I want to invite you all to come to the Earth next year for our 31st season of the Wonders of Physics. But for now, thank you all for coming.